Hello and welcome to part 3 of the video tutorial on the 2008 Electricity and Electromagnetism exam. So this is question 3, which is on electromagnetism. And we have this diagram here, which is of a wind-powered generator in a yacht. So we've got a north and south magnet causing a magnetic field here. And we've got this coil of wire, which is on an axis, spinning around. That's all we really need to know, because this circuit isn't connected yet. That's probably going to be connected in the next question. And they give us all the information we should need here. The length and width of the wire, which is in centimeters, so probably the first thing we need to do is convert all of this into meters. So this is going to give us 0.64 meters and 0.06 meters. 0.064 meters and 0.146 meters. Tesla is the correct unit, and this is in centimeters again, so we're going to want this in meters, so this is going to be 0.20 meters per second. Right, we need to calculate the maximum induced voltage across one loop. So if we look at our formula sheet, we've got the voltage here. Voltage equals the strength of the magnetic field times the velocity times the length. So that's going to give us V is equal to BVL, which is, so we've got the strength of the magnetic field, 0.75 times the velocity, 0.2. And with the length of the wire here, it's asking for the voltage across one loop, so that means one whole loop of the wire. So we're going to have both the lengths of the wire included. So we're going to take the length, AD, so times 0.146 times 2, and that should give us the right answer. 0.75 times 0.2 times 2 times 0.146. Okay, so that looks about right. Because there's not going to be a lot of voltage across one loop. Basically, well, I'm just guessing here, but because the strength of the magnetic field isn't that much, and there's 100 turns of the coil, so if there was a really high voltage in one loop and they're timesing it by 100, you're going to end up with a really, really high voltage. So this seems like a reasonable answer. So to the right number of significant figures, this is going to be 0.044 volts. Okay, better put it there. Describe 3 ways in which the size of the induced voltage across the length of the coil can be increased. Well, if we just look at the formula here, we have three aspects. We have 3 things in the formula. So if we increase this, if we increase the strength of the magnetic field, then the velocity will increase. Sorry, the voltage will increase. If we increase the velocity, the voltage will increase. If we increase the length, the voltage will increase. So we just need to increase the magnetic field strength, or the strength of the magnetic field. Increase the velocity of the coil. So that basically means spin it around faster, and then it'll generate more voltage. Increase the length of the wire, or the length of the coil. Right? Okay. Part C, state the position of the coil that produces the maximum voltage and explain why the size of the voltage changes as the coil rotates. So, I'll use this diagram here because it's basically the same. So, we have, this is going to be rotating, so we need to find what position the coil needs to be in that produces the maximum voltage. And that's going to be when the coil is perpendicular to the magnetic field, like a right angle. And the reason for that is, looking again at our formula sheet. So this here, this is the force felt, so we need to write this properly, it's actually times sine theta, but a lot of the time the angle is going to be perpendicular, and sine of 90 is 1, 90 degrees is 1, so you don't need to use that. But when we're finding the position of the coil, that's going to be when it's perpendicular, so when this is the case, because otherwise, when there's an angle here, this is going to be less than 1, so you're going to be multiplying by decimal, so the force felt, and in the same case the voltage is going to be smaller because of the position. It's not at a perpendicular angle, and if they were parallel, then this would be 0, so it would be sine of 0, which is 0. And then you'd end up with nothing, so there wouldn't be a force felt, and there wouldn't be any voltage generated. So when the coil is perpendicular to the magnetic field, then it will produce the maximum voltage. Explain why the size of the voltage changes as the coil rotates. So, well, basically, like I said before, when the coil is parallel, there'll be nothing. There'll be no force felt, no voltage generated. And when it's perpendicular, that'll be the maximum. So the angle of the coil in relation to the magnetic field. Oops, in relation. Will change the voltage generated, or the force experienced and the voltage generated. The voltage will be minimum. When the coil is parallel. To the magnetic field. Hopefully you can understand that. The generator has been modified, or can be modified, to act as a DC motor by changing the slip rings to a split ring. And that means, so we have a battery here now. Yep, the motor is connected to a 12-volt battery. And they're telling us the resistance of the coil. and the coil still has 100 turns. So now we need to calculate the maximum force acting on one side of the coil. Okay, so we need to calculate the force. So we're going to use what we had before. So force is equal to VIL. Right, this one here. And we're just going to assume it's perpendicular because they don't tell us anything otherwise. So we'll be using the standard formula. And we have the strength of the magnetic field, that hasn't changed. And we have the length. And this time it's asking for one side of the coil. So we'll only be using one length, because in the last example we did the entire coil, but now we're only doing one side. So this means, but we don't know what the current is. That shouldn't be a problem because they give us the resistance and the voltage. So if we go I is equal to V over R, which is equal to 12 over 4.5. So 12 divided by 4.5. Okay, so that's 2.66. To SF. Amps, or amperes. Then that means, so the force is going to be 0.75 Tesla. That was from the last example, but that hasn't changed. Times 2.66 times the length, which was 0.146 meters. And I think we're going to have to apply the 100 turns here because it's asking for one side of the coil, but it's the full coil. So times 100. So I think that's what we're going to do. 0.75 times 2.66 times 0.1. So that gives us 29.127. So this is equal to 29 newtons. And that's the end of the exam. I hope that was somewhat useful. And hopefully I'll be doing more videos, so I'll see you soon.